Since now it's 11, people will just come in. So I will just say some opening remarks and Jan will introduce you. Okay. So good morning, good afternoon, or good evening to everybody joining us from around the world. Thank you for being here with us today. I'm Mary Salvana, Assistant Professor in the Department of Statistics at the University of Connecticut in the United States. On behalf of the organizing team, I'm pleased to welcome you to the High Performance Statistical Computing, or HPSC, presentation series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them during the Q&A. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We typically host one seminar each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources at hpsc4science.org. Before we begin, I'd like to briefly mention that we also have an invited session at the Joint Statistical Meetings 2026. The session is titled High Performance Statistical Computing: Challenges, Opportunities, and Future Directions. The session will take place on Thursday, August 6, 2026, from 8:30 a.m. to 10:20 a.m. in Boston, Massachusetts. We would be delighted if you could also join us for that session as well. With that, I'll turn it over to my fellow organizer, Yan Song, to introduce today's speaker. Go ahead, Yan.
Hey, hello everyone, I'm Yan Song, Assistant Professor at the University of British Columbia and co-organizer of this HPSC seminar series. It's my pleasure to introduce today's speaker, Dr. Alexander Litvinenko. Alexander Litvinenko received his PhD from the group of Professor Wolfgang Hackbosch at the Max Planck Institute in Leipzig, Germany, where he worked from 2002 to 2006. He then held a postdoctoral position at TU Braunschweig from 2008 to 2013, followed by a research scientist position at King Abdullah University of Science and Technology from 2013 to 2018, where he worked across the areas of uncertainty quantification, extreme computing, and computational Bayesian statistics. Since 2018, he has been at RWTH Aachen University. In 2025, he completed his habilitation titled Low-Rank Tensor Methods for PDEs, Data Analysis, and Spatial Statistics. His research interests include numerical methods, spatial statistics, uncertainty quantification, tensor methods, and computational Bayesian statistics. With that, I'm happy to turn it over to Alex to begin his talk.
Thank you very much, and thank you very much for this introduction, very nice introduction, and this opportunity to present our joint work. I start this work during my stay in KAUST, and problem setup was done by Mark Genton, Ing Soon, and they were responsible for statistical part. And my strong background is hierarchical matrices, so it's a technology how to work with big matrices. We will speak about this later. And I would like to present a topic, the slides. So this work, identification of unknown parameters and prediction of missing values, comparison of approaches. Okay. So just motivation. I collected on this slide main facts that you will learn, you will see today during this presentation. So you will see how we work with very large covariance matrices. So very large, I mean 2 million rows, 2 million columns. We approximate them with hierarchical matrices. You can see on the right a lower part of covariance matrix. And you will see that we are able to reduce storage cost from 32 terabyte just to 16 gigabyte. We will be able to do Cholesky factorization of covariance of dense covariance matrix, compute its determinant, inverse, just in 8 minutes on modern desktop computer without any supercomputer. You can see also random field which is taken from first statistical competition from KAUST organized by Sami, Genton, Ingsun, and David Kiss, and maybe somebody else. And here we try to identify unknown parameters from Matern covariance matrix. Okay, about details we'll speak later. Practical motivation example which we use in this paper is example from which I received from Ingsun and Mark Genton. This example, it's about high resolution daily soil moisture data at the top layer of the Mississippi Basin. So it's a stationary problem, no time dependence. So we have satellite data, maybe pre-processed satellite data from this area. And in total, we have about 2.4 million locations. 2.1 observations are known, and we have 278,000 missing values, and our task is forecast these missing values. They are somewhere distributed in this dark area. This dark area is about 1,000 kilometers times 1,000 kilometers geographically. It's a part of Earth. Okay, the structure of this talk. I will start with motivation. I said already some of this motivation. Then we set up problem. We speak about identification of unknown parameters via maximizing Gaussian log likelihood. It will be easier because it's very similar what, for example, Ingsun presented in her talk. It's just easier than it was in her presentation. Then we speak about hierarchical matrices. Not everybody knows this. Yeah, then we speak about error analysis. We do prediction, and then we compare hierarchical matrices with other methods. For example, decision trees, neural networks, and nearest neighbors. So all of them we can define as machine learning methods. So this slides is probably well known to you. So we have S1 and so on, Sn locations, n is could be 2 millions. So we have Gaussian random field indexed by spatial location S. So in our case, it's moisture, for example. So we do some assumption. We say that random field Z has mean 0 and stationary parametric covariance function. So there are many possible covariance functions. We just fix a class, Matern, and parameters, smoothness parameters, covariance lengths, nugget, and variance, sigma, they are unknown. So now task is to identify these unknown parameters. So we define all these 4 parameters like a theta bolt vector. So for this, we formulate, build log likelihood function. It's written here, also very well explained by Ingsun in her presentation. There are 2 difficult ingredients here. One is log determinant of large covariance matrix, and another is quadratic form here. That is our data. So it's a non-linear function. It's already non-linear with respect of covariance matrix, but parameter theta for parameters, they're also non-linear. There is also non-linear dependence of these parameters in C. So another strong assumption that this covariance matrix depends on distance, yes? As it's Si and Sj 2 points in the space. So we are now next, our task will be to compute maximum or minimum of this function and find where this minimum is achieved. So we define it with theta hat. Okay, we are going to use hierarchical matrices to approximate covariance dense covariance matrices here. And here already some example so that you know what is to expect. Because covariance matrix is symmetrical, it's very typical that we compute only lower part or lower triangular part of this matrix. And this is what you see here. And the small numbers inside means rank. So for example, here in the middle, rank of this block is 6. So it could be a very large block, like maybe 100,000 times 100,000, and it's approximated with rank 6. White blocks are 0 blocks. Also, what is important, and what is a big advantage of hierarchical matrices, when we perform linear algebra operation with these matrices, we preserve format. So in the middle, you see Cholesky factor of original covariance matrix, and they're slightly different. For example, here is 5, here is 6. It's a different matrices, but format is preserved. And if you zoom this corner, you can see this picture. Red blocks, dark blocks, they are computed exactly, they are not approximated. And this stairs, or here, this what you see inside of red blocks, it's a decay of singular values. So it's very important that decay is fast, yeah, in log scale, decay in log scale. So for example, this block has rank 14, this block rank 7. So now question is if H matrices always work, and answer is positive, but the worst case scenario is that even in subblocks which are far away from singularity, from diagonal, it can happen that singular values decay very, very slow, exactly like we saw it in this. So even though we have excellent decay here, but rank is, for example, in this block 90. In this blocks 119, and rank can come quadratically or even cubically to all memory or computational cost estimations. So rank is crucial, and we are interested to keep rank small, of moderate size, between 5 and 20 maybe. So here everything is good. Okay. Of course, when we approximate original matrix by its H matrix approximation, denoted by CH, calligraphic, we should ask ourselves how determinant of matrix C change. Probably many of you know that these examples from linear algebra, you do small perturbation in your matrix just in one element, and then inverse explode, determinant explode, and your numerical algorithm become unstable. Then later we will compute Cholesky factorization, and of course we should control approximation error and Cholesky factor. The same for inverse, and we would like also see how original log likelihood L calligraphic differ from its H matrix approximation denoted with tilde, and K means rank, so it's maximum rank in the block, in subblocks. So we can say, for example, here number 20, it means that we guarantee that maximum number which you will see in green blocks will be 20. can be smaller, but maximum is 20. So usually we do it when we have limitation in memory on our computer. For practical computation, it's better to have adaptive rank, exactly like it's here. Adaptive ranks means that we, a priori, at the beginning, we say that we would like that accuracy in each sub-block is 10 power minus 6, for example. And then, of course, in every block, you will have different rank. And in this case, you see 7, 5, 14, it's different ranks. But accuracy in every sub-block, it's the same. It's, I do not remember what this was here, but something like 10 power minus 8, maybe. And finally, we would like to know so how estimation of theta, this vector which we try to identify, differ from from estimation which we receive after applying H matrix approximation. For this, we do not have theoretical answer, only numerical. Okay, a few words about hierarchical matrices. What is the idea? Idea is that you have, you take your covariance matrix and you divide it into sub-blocks. For example, here it's binary division. You divide number of columns, number of rows by 2, and then recursively you divide every sub-block. In this case, we decided to divide only diagonal sub-blocks, just an example. And this is binary tree which describe this block partitioning. We call it block partitioning. And then we have some heuristic results to approximate every block separately. So for example, if we see that it's hard to approximate this big block, we divide it further and try to approximate every smaller sub-block with low rank matrices. For this, we can use either truncated singular value decomposition, or maybe randomized singular value decomposition, or maybe some heuristic like adaptive cross approximation methods. So this is the idea of truncated singular value decomposition, why it's work. This is actually a slide which explains why H matrices, the kernel of H matrices. So every green block is approximated with truncated singular value decomposition, and assume that this block is M, yes? And you compute singular value decomposition, so you have matrix U, matrix sigma, matrix V transpose. It could be rectangular matrices in general. And very often we do observations that singular values decay very fast. And we can say, for example, that all singular values smaller than 10 power minus 6 are 0. So we put here a very big 0 in sigma. And then because here is 0, no need to store this old white columns here and all these rows here, because anyway, we multiply with 0. And then instead of upper picture, we have lower picture. So we have M tilde, it's approximation. And then we store only K columns here, K rows here, and K times K matrix here. So typically we can keep only, let's say, 10 largest singular values from 1000. Okay, there are plenty of different block partitioning. This is one of them, but it's this block partitioning, it's a NP-hard problem to find best block partitioning. And everything what you see in this work and other, it's heuristics. This block partitioning may depend on geometry, on how much memory you have of your of your discretization or location of your measurements. Yeah, if your measurements are equally distributed, or maybe they are localized in some corner. In standard H matrix library, there are like at least 3 or 4 different, maybe more, strategies how to do this block partitioning. Yeah, another ingredient is admissibility condition. So it's exactly tell us which blocks can be approximated by low rank matrix and which block not. So idea is we assume that this is a block of our covariance matrix. T, it's a cluster which corresponds to location, spatial location. This another spatial locations. And we see how far away this spatial locations are in nodes of this figure. So we compare diameter of this box, diameters with distance between these two boxes. So we actually say how far these locations from these locations. And if they far away, means that they do not influence too much each other. So covariance between them is weak. And we may approximate this covariance between these two sub-regions by low rank matrix. But you do not need to think deep about this. It's everything automatically implemented already in H matrix. So just show you advantages of H matrices. So building of H matrix cost n log n. Log n appears because you have this recursive subdivision into subblocks. Storage is kn log n. If you parallelize, you have on P processors, on shared memory, you have these estimations. And you see here, for example, here you have k square. So if your rank k is large, let's say it could be 100, then k square it's already 10,000, yes? And this may already be comparable with n. So I repeat again that actually H matrices work always, but if k is large, then they become like just a bit cheaper than dense matrix arithmetic. So no point to use them actually, with in other words. Okay. It's a slide about notation. So we have covariance matrix, which depends on parameter theta. So we use Brent method, which combine bisection method, secant method, and inverse quadratic interpolation. This is not modern. It's very old method. We just took it. And this is gradient free. Of course, you can also use for, we are going to maximize likelihood function. And of course, we can use gradient to reduce number of iteration. It's a possible, but then H matrix, then instead of one H matrix, we have at least 4 of them. So we need to set up all these partial derivatives, and it's also cost. And at the end, it's not clear if gradient will really improve situation. So for simplicity, we implemented without. If you need, I refer here to works of Mark Genton, Ingsun. In their work, I saw all this accurate implementation with partial derivatives. And in our preprints, we also have these formulas. Okay. To simplify, we compute Cholesky. It's written in second formula here. And then instead of computing inverse, we inverse Cholesky. It's much cheaper. And actually, we do not inverse it. We solve corresponding linear problem. And it means that we need to solve linear system and then compute scalar product of two vectors. It's just much cheaper than compute inverse. then we can reformulate logarithm of determinant in this way. Instead of C covariance matrix, we write a Cholesky. Then determinant is a product of diagonal elements which we see on Cholesky. So once we have Cholesky, we simply take diagonal elements. They are not singular values, but product of them give us determinant, because matrix is upper or lower triangular. And then logarithm of this product will be this sum. So actually we can simplify our original log likelihood and it become 2. Here we have some theoretical estimations done by Jonas Balani, Kressner, Ibsen. So if spectral radius of this matrix is smaller than epsilon, this is typical way how they measure error approximation in H matrix. Then log determinant of C minus log determinant of C tilde, it's H matrix approximation, can be estimated theoretically by this. And numerically, they observe that, Kressner and Balani, that N is pessimistic and it's not really observed numerically. So then we can also do some assumption for our data, and then we can estimate difference between original likelihood and or absolute error, if you want, and its H matrix approximation. And the formula is here. Yes. So this formula practically tells us that if our H matrix approximation of Cholesky or inverse is good, then everything is good. Okay, here it's the first numerical results. So we have accuracy inside of each block. So for every block, we fix accuracy, relative accuracy. No, absolute accuracy, I think. And this is here, and for different covariance lengths here. So size is not impressive just because why? Because I compare what we compare in second column, logarithm of determinant of original matrix, dense matrix, with hierarchical matrix. So if I take n bigger, it's peanuts for H matrix, but it's not peanuts for dense matrix arithmetic. So I practically cannot compute this guy. So it's original matrix without any approximation. So I will be not able to compute this difference. And you see that if we increase accuracy in every sub-block, we can approximate it very well. So it's a good result here. Absolute error, relative error, Frobenius norm, relative spectral norm, way how we compute Cholesky and inverse. And this is compression rate. So this preliminary numerical results give us promising, and we do not see anything suspicious here. Okay, next slide. We try also estimate covariance length, smoothness, variance, and it's better to read these plots from right to the left. So we start with 2000 observations, measurements, or locations. Then we switch to 4000. And of course, the more data you take, the more accurate are your results. And of course, here we will see it later. And actually, we saw it already in first slide. We should ask ourselves if really we need this 2 million observations. Maybe 32,000 is already enough. And here, for example, you see that red line is median, and this is it's 50%, 25 and 75% quantiles, green lines. So already with 32,000, we receive good results, at least for this data set. Okay, some further numerical results with already some significant number of observations. So our matrix is 2 millions times 2 millions. So computational time is here. You see it's only 229 seconds, so like 4 minutes to compute matrix. We need approximately 15 gigabyte memory, and most important is to control kilobyte per degrees of freedom. So these big numbers tell you not so much, but this, in ideal case, this number should be the same or increase just a little bit. And we see here that it's increase, but very moderate increase. And it's not enough, of course, only set up matrix. It's important to see behavior when we compute Cholesky. So what may happen? You approximate your matrix and everything is nice. But then you compute inverse or Cholesky, or you try to compute and you fail because ranks and sub-blocks become very big. But here we see that everything is again under control. Of course, Cholesky, it's slightly more expensive, than 2 times more expensive than computing of original matrix. It requires also 25% more memory, but it's everything under control. Errors also acceptable. So everything was done on just Dell Station desktop computer on with 40 cores, 128 gigabyte RAM. Okay. Of course, when we work with practitioners, they do not need estimation of parameter theta, they need prediction. So here we see that all our data divided into subsets, which Z1 what we know, Z2 in location Z2 we do not know our moisture, let's say, and we would like to do prediction for Z2. So in example above, here we had dimension of Z1 was 2 millions, and this was 0.2 million, 200,000. Of course, then we can represent our covariance matrix in block structure, and we can compute our predicted values can be expressed like here. It's a well-known result, nothing special here. And covariance matrix, conditional covariance matrix is here. So by the way, this is very good related with numerical methods for partial differential equation. This guy called Schur complement, and in numerical mathematics, they do this operation very often. So now a few words about chaos competition. So we participated in first chaos competition on spatial statistics for large data set. All these links are still working, I check. So if you click here, you come to description, final paper, where Sami, Mark Genton, David Keith, Ying Sun, very nice summarize all results. So here you can see our paper where we describe our results. So we used, of course, H matrices, this likelihood, maximum likelihood, and we also used K nearest neighbors, short KNN. So for each X, variable X, location X, we check K nearest neighbors, can be some 3, 7, or maybe 200 neighbors with respect to some metric, and set predictions that our prediction is average among neighbors. So difficulty here is only to find the right number of neighbors. And we tried different number of neighbors from 1 to 20. And we choose best one. We also try random forest. So it's a set of decision trees. A large number of decision or regression trees are generated independently on random subsamples of data. The final decision for our prediction is calculated over the ensemble of trees by averaging the predicted outcomes. Also, it's not clear how many trees are optimal, so we try different numbers of trees between 100 and 150. And we also try a deep neural network. So input layer consists of 2 neurons, input feature dimensionality, latitude, longitude, and output layer consists of 1 neuron, predicted feature, and moisture. So we examined a few variants of fully connected neural networks, architecture for 3, 4, and so on, 10 hidden layers with 50, 100 neurons in each hidden layer. Yeah, and next slide, you will see already results. So data were provided by KAUST, by Sami, Genton, and so on. And it was small data set and big data set. They were divided by 10% and 90. 90% were used for training and 10% for evaluation, testing. So KNN method showed the best cross-validation results over 100 runs. So we found that optimal number of nearest neighbors 3 is optimal. For test 2A, it's a small data set with just 100,000 observations, and number of neighbors 7 was optimal for 1 million locations. It's a bigger data set. So we observed that 120 regression trees is optimal. Fully connected neural network which we used was 7 hidden layers with 100 neurons in each layer. Number of epochs 500, batch size 10,000, and so on. So time, surprisingly, k nearest neighbors work for this provided data sets very well, very fast, so 0.07 seconds. So for a random forest we had 12 seconds, and for fully connected neural networks we had 173. So because its efficiency, we decided further to run only KNN. They were more accurate and very fast. So here, for example, you see random field, one realization of random field predicted by k nearest neighbors for small data set with just 100. So this is big data set. Yeah, 2B, so big data set. So we use 900,000 locations to train and evaluate it. So blue points are 100,000 blue points here, and blue points are our prediction. And as you see, they fit very well to this surface. This result were received by hierarchical matrices and likelihood estimation. So how we started this talk with approximation of log likelihood. And you see results are less accurate. So what is a possible problem here? Still acceptable, but less accurate. Yeah, because in this method, we have some intermediate step to evaluate theta. So this covariance length, smoothness, nugget, variance, and there are many possible. So log likelihood is very flat, and it means in many points you can achieve gradient which is almost zero, not zero, but almost zero, let's say 10 power minus 6. And then to do forecast, you take not best parameters. And then this is my hypothesis. Maybe there is some other reason, but this is possible explanation. Okay, this is prediction by it's another data set. So you see data set are different shapes of this different. Again, KNN provided excellent results. Blue points align very well to yellow surface. H matrix maximum likelihood method also provided very good result. Cannot complain. Similar results for smaller data set. You see everything is again. So blue points are our prediction. So fit very well to the yellow surface, which is constructed by 90,000 locations. It's just visualization. No need to compute yellow surface. Just visualize. Blue surface was computed here. The same for hierarchical matrices and maximum likelihood estimation. So our method, which we presented. Another data set. Everything also nice with H matrices. Another data set, number 7, also they were rather small. So we use this root mean square error, and maybe this is good table. You see this summarize results. So test 2A is a small data set with 100K, test 2B big. So this small data set, best results were achieved by hierarchical maximum likelihood, exactly our method which we presented. And for big data set, surprisingly, KNN provided very good results. Also, HMLE, so our method for this second data set, also very good result. For random forest and neural networks, this 1 million was too much, not enough memory. So we have two leaders here. KNN, by the way, in one of category in the spatial statistic competition, KNN took second place. Okay, I conclude. With H matrices, you can approximate covariance matrices. For example, maternal. That's good news because it was not automatically clear. So we can approximate Gaussian log likelihood. We can identify known parameters. Ranks stay under control. Nothing else explode. We can do prediction. So, of course, MLE estimate depends and prediction depends on H matrix accuracy. Third point, it's rather what I would say negative, that we have multiple good candidates for theta, and not all of them deliver good predictions. So we provided some theoretical estimates for H matrix. So we also know that each machine learning method needs fine-tuning stage to optimize its hyperparameters or architecture. We are positively surprised by very easy method KNN, which is easy to implement, and it's provided on this provided data sets promising results. So open question, just few words. Yeah, data which are repeating data, this is a problem for matrices, because what does it mean? Two close locations or two repeating measurements in the same location. It means two linear dependent rows or columns in your matrix. It means that your numerical methods will fail because matrix is not invertible. Cholesky cannot be computed. So one should kind of filter out repeating data. We also need a good starting point for optimization. And H matrices become expensive if it's 3D, already in 3D, in 4D, or if number of parameters more than 2 or 3. I upload all these libraries here. You can click, everything is link work, and yeah, because so my suggestion is for future to try to combine hierarchical matrices with tensors. So here you see tensor product of covariance matrices. One could be spatial, another could be temporal statistical covariance, temporal covariance matrix, and we can reformulate log likelihood in terms of tensors also. Of course, it can be done easily only for rank 1 tensor. If it's rank more than 1, it's become harder. Yeah, here we have some, even you can compute Cholesky, and you can compute inverse of this tensor product. You can compute log determinant if it's tensor of rank 1. And it's much faster. All this, you can compute diagonal, trace, determinant, log determinant. And this is example of tensor product of 2 Cholesky factors. So in every blue small triangle, it's a big matrix. Another interesting idea is domain decomposition technique. So you take, we do spatial statistic, and we decompose our original domain into subdomains and compute hierarchical matrix or covariance for every single subdomain. And then we get covariance matrix which looks like this. So we have a big block which is diagonal and some weak coupling. And there is excellent hierarchical matrices algorithm for this. This is, for example, how you can compute inverse. Another, I'm almost done. Another what is very interesting is to consider multi-scale random fields. So here I refer to Howard Ruhe, Finn Lindgren, and David Bolling. Here coefficient kappa can vary across scales, can diffusion can oscillate, and this is excellent for hierarchical matrices. It's exactly what people are doing in numerical mathematics. It would be nice to apply this experience here. So thank you for your attention. I'm done.
Thank you very much, Alex, for this wonderful presentation. We have about 15 minutes for question and answer. If you have a question, please feel free to unmute yourself or type it in the chat. I will read the questions a lot so everyone can hear them.
I have a question, Alex.
Yes,
If,
please.
if KNN works really well, how do we convince people to still do Gaussian process?
It's excellent question. It's exactly what I ask ChatGPT many times to find good examples. I even implemented this. KNN, for example, fail in anisotropic case, or when covariance lengths where not only short-term effect but long-term behaviors become important. So practically you may need not 3 neighbors or not 10 neighbors, but 10,000 neighbors, and then KNN will fail. You know, it should not surprise us or be negative. If data set is very easy, simple, then of course many methods will work, and it's not surprisingly. And we just need to apply right methods for the right problems. And if data set is simple, I recommend to use KNN. I also recommend to use Vecchi approximation. It's even faster than hierarchical matrices. But in my case, for example, I come from numerical PDEs, and my tool which I use a lot is hierarchical matrices. And it's for me, it's natural to use hierarchical matrices.
I have I also have a question about this KN part. So have you ever like compare the uncertainty quantification of this KN and likelihood method based on this H matrix?
No, sorry, we didn't.
Okay, thank you.
So, I mean, you know, in this data set, in this
Yeah.
competition, they ask us to provide certain, it was not only this, it was two other errors, I think, and we just reported this. And it's a good question. Maybe Sami and other organizers should think about uncertainties in the next competition if they plan any.
Okay. We have a question from our audience. Could you please show the slides with the references again?
Yes. So I just comment that in first we have this, it's a technical report where we report this machine learning methods. And these two papers illustrate hierarchical maximum likelihood estimation. One of these papers is technical, describe in this two in method X, describe technical details, how we implemented everything, and paper 3, it's more theoretical one.
Have you also done non-Gaussian data?
Excellent question, actually. Maybe you ask something different, but we try covariance matrices which depends not on distance, but just on x, on one x and y, not on distance between x and y, but x and y. And H matrices, let's say, covariance matrices equal minimum between x and y, or maximum, or something like this, and some other, and H matrices works, yeah, very good. They even these matrices were very long, very low rank, rank 1 or maybe 2. So we didn't do estimation of parameters, but we try not only stationary covariance matrices, but other types, and results were promising there. But I'm not sure that it was your question.
Yeah. I mean, when there are like outliers or heavy tails or something. Non-Gaussian data, but yeah, I guess as long as there's covariance matrix.
I guess some data in second competition were fed tails. They were not all of them were Gaussian, and this is maybe why it took for us more time than we expected. Some tuning is necessary. So H matrices will work. This is my guarantee here, but it could be poor estimation of parameters, of matern parameters, without extra tuning. Maybe some as initial better initial guesses needed, or so when I from numerical point of view, if I look on likelihood, Gaussian multivariate Gaussian log likelihood, not data is a problem, but not data Z, but covariance itself is a problem. So very often I cannot invert matrix, I cannot compute Cholesky because covariance length is very small and singular values or diagonal elements are close to 0, or very unstable computation of determinant, it's because it's 0, for example. And a good question, we discussed it with Mark Genton. Are we allowed to use this log likelihood if data are not multivariate Gaussian? And maybe I'm wrong, but what I think still, even though the theory says that you should use this log likelihood for multivariate Gaussian, but you can also try to use if data, not strictly speaking, multivariate Gaussian, it still may work.
Yeah.
Okay. Hello, Alex. I have another question. It's about the multi-scale random field. Since, like, based on my understanding, I always feel like for this Markov random field, we use sparsity technique. So how does H matrix used in that?
Exactly.
Yeah.
So you're completely right. If you approximate this object, this is actually, if I is 1, this is Laplace operator. In 1D, it's a 3 diagonal, 5 or 7 diagonal. Sparse matrices are faster than hierarchical matrices. So if you can use sparse matrices, they are faster. But here you have, you may need inverse or even alpha could be fractional power, yes? And this, when you compute this object, it is already not sparse. So everybody knows that square root of Laplace, it's a dense matrix. And sparse matrices will not work. So you should, but why I put it here, because this object is very, very well known in numerical methods for PDE society, numerical method. And this diffusion equation is solved very often. And they approximate with tensors, with H matrices, this fractional power of Laplace also very often. They also pay attention to this oscillatory coefficients, because method by default may fail with oscillatory coefficients, because your conditional number of your matrix depends on this coefficient. But number of iterations, which, you know, Howard Ruhe and Lindgren, they use iterative methods to solve this PDE and to get this random field. And they need iterations, and number of iteration is proportional to square root of conditional number. And this conditional number depends on this. And for strongly oscillatory, it could be conditional number easily can be 10 power 8. So it means that you need 10,000 iteration to compute U.
Okay, thank you.
Thank you for questions.
Do we have any other question? Okay, if not, then I think that's about it for today. If you have additional questions for Alex, please feel free to reach out to him via email. I'm sure he would be happy to continue the conversation. We will be posting announcement for our next seminar soon, so please keep an eye on your inbox and our website for updates. Thank you all for joining us today. We look forward to seeing you at our next HPSC seminar. Okay, bye-bye, and thank you, Alex.
Thanks, Alex.
Thank you very much. Thank you.
Thank
Thank you
you.
for your attention. Have a nice day.
Yeah, you too. Have a nice day.